Okay, so this lecture is actually under, um, it's under relationship theory. So today we're going to be talking about time rates. So just a little forward. This is not going to involve some heavy mathematical machinery. Just a little bit of analysis. So let's start with two partners, Alice and Bob. And let's say that they used to be in a relationship, and then now they're separating. So at one point, in time, or space time, they used to be at a single point together, and then now they're separating from each other at some rate with respect to time. So let's say that Alice is moving away from the initial starting point where they used to be at 5 meters per second. Yeah, I know it's very fast. Let's say they're driving a car, and let's say Bob is moving away at 1 meters per second. So so if I let the distance from the starting point with respect to time be a of t, so this would be a of t for Alice, and this would be b of t for Bob. So what I'm saying here is that a of t is the distance that Alice has traveled with respect to the starting point. And b of t is the distance that Bob has traveled with respect to the starting point. So we can say that 5 meters per second here is dA divided by dt. And the 1 meters per second here is dB by dt. So the goal of the problem now is to find out how fast they are separating from each other. Not with respect to the starting point, but from each other. So I'm going to call this C of t. So what is dC dt? So primarily, we have A of t and B of t. So collect, if I collect d of A and dA dt and dB dt, in fact, if I just collect A of t and B of t into a column vector, or if I say f is equal to A of t times the I hat basis vector plus, no, actually this is j hat plus B of t I hat, then we have a vector field. This is a vector field, and my corresponding df dt is another vector field, which is composed of all vectors, so velocity vectors of Alice and Bob. So this actually forms a slope field. This is a slope field. This is just a regular old vector field. And so for DC, we actually have some initial conditions. So it also states in the problem that we are to find dC dt at 5 seconds. So 5 seconds. So what is dC dt at 5 seconds? So we have some primary data. And we're going to be considering two cases here. We're going to consider the case wherein they're separating from each other. So Alice and Bob are separating from each other at right angles. And we're also going to consider the case wherein they don't separate from each other at right angles. So if they don't separate from each other at right angles, we're going to have to consider the cosine law But because they're separated at right angles from each other, this here forms a right triangle, and we can exploit Pythagoras' theorem. So a of t squared plus b of t squared is equal to c of t squared. So in the slope field, or in the vector field formed from a to b of t, each vector depends on an instant in time. So at every instant time, depending on like how well they're separating or their acceleration of the vehicles, a of t and b of t changes as time goes on. Okay, and so notice that because a of t and b of t change, that means that their squares also change. And because their squares also change, the sum of their squares also change, and so c of t also changes. So we can't say in the beginning that c of t changes and it's a constant. Well, in the end, yes, dc dt will be a constant. It's gonna be some scalar value, which tells us the speed, right? But right now, it doesn't change. So we're treating it as a function. So that means when we take the derivative of this expression, c of t squared does not vanish. Neither does a of t and b of t. So that's what we're going to do next. Because we're trying to find dc dt, we're going to take the derivative of both sides. So the derivative of this expression, or this equation, gives me 2a of t dA dt plus 2b dB dt is equal to 2c dc dt. So I'm just abbreviating it to a, b, and c, so it's much easier to see. So now 2 is on all expressions here, so I can just divide that out and make it vanish. So I have a dA dt plus b dB dt equals c dc dt. So you guys can already see dc or dt here. You can just divide by c. So dc dt. So I'm just gonna move things around using the commutativeness of the equation symbol. So dc dt is 1 over c, or I think the transitiveness, dA dt, so a dA dt plus b dB dt. So now all we have to do is plug. But the thing is, we don't quite know what c is yet, or a or b. We don't know what they are. But we do know dA dt and dB dt. So how do we find c, a, and b? So we're going to exploit the fact that the derivative is velocity, right? In this case, it's velocity. Or it's the speed. And speed is a rate, which is the distance divided by time. And we know distance. In this case, we know distance right now. And the distance is precisely our functions a of t, b, and t, and c of t, respectively. So we can say that dA dt is a of t divided by the time. And dB dt is b of t divided by time. And we're trying to find dc dt at 5 seconds. So 5 seconds is something that we could use in this case. We know dA dt, we know dB dt. We're not going to say dc dt is equal to c of t over t, because we don't know a lot of things in that equation or that relation. So the only useful relations would be dA dt equals a of t over t, and dB dt equals bt of t. So b of t over t. So we have that. Yeah, Jesus is trying to call me to him. Okay. So dA is 5. So that's 5 is equal to a of t over 5. And dB dt is 1. And then over here. So that's dB dt. That's b of t over 5. And so rearranging, we have that a of t is 25 So this is meters. And B of t is 5 meters. So now we know A of B, then B of t. How about C? So let's go back to the relation a squared plus b squared equals c squared, Pythagorean theorem. Because we know A and B, we can now calculate C of t. So C of t is simply the square root of A of t squared plus B of t squared. And that's 25 squared plus 5 squared. And you guys can grab your calculator to calculate this one. I don't have mine. So you guys will find that C of t is, so it's 25 squared plus 5 squared. Try to express it in radical form, damn it. So it's some number. So I'm just gonna calculate 25 squared here. So 625 plus 25. So that's square root of 650. So let's see if we can divide this by any perfect squares. So that's actually 25 times 26. So it's 5 root 26. Okay. So 26 cannot be divided further, I believe. Yeah, it can't be divided any perfect squares anymore. Okay. So 5 square root of 26 meters. Yeah, I have to do things a bit manually here because I don't have my scientific calculator with me. But that does not matter. Okay, so we now know C of t. We know A of t. So in the equation we know C of t, A of t, dA dt, B and dB dt at 5 seconds. Okay, so this does not work for all t. This only works for 5 seconds. Okay, so actually I should say that this is at 5 over here. But yeah. So that's 1 over 5 square root 26. And then A of t is 25 times dA dt at 5 seconds is 5 plus 1, which is B of t, and times 5. So if you punch that into your calculator, 26 5 times 5 plus 1 times 5. You find that dc dt is precisely 5.0990 meters per second. So Alice and Bob are separating from each other at precisely 5.009 meters per second. So that's assuming that the separation is at a right angle. So what if it isn't at the right angle? So let's say it's some angle theta. Okay. And this is Alice. And this is Bob. So it's a vector. So what is my C of t now? Well, it's actually going to be the same procedure, except we're going to tack on an additional term, which is precisely minus AB cosine theta. So this time, instead of using the Pythagorean theorem, we're going to be using cosine law. So the relation we know is that c of t squared is a squared. So I'm just going to write it in terms of a and b instead of a of t. So a squared plus b squared. So you guys will still need to keep in mind that a and b are still they're still functions of time. So they're not just constants in this case. Okay, so a squared plus b squared minus 2ab cosine theta. And when you derive this, you have that 2c dc dt. So we take the derivative with respect to time. It's just the same thing, 2a dA dt plus 2b dB dt minus 2. So the thing is, now I have to use the product rule with three guys. So I'm gonna take the product of this first. So the product rule of a and b. So left a dB dt plus b dA dt, and then the cosine. So cosine theta. But the thing is, okay, it's not really cosine theta is not changing in this case. So it's not gonna be some complex movement wherein they're gonna be like moving this way or that way. They're just separate at each other at constant like sort of velocity, I suppose, or speed. So cosine theta doesn't change in this case. Although you could say it could change, and then I guess you could try to calculate theta in this case. But calculating theta shouldn't be that bad since we know our initial conditions. And once we know c of t, we can sort of find our cosine theta or our theta using this relation, of course. But in this case, we're going to assume that cosine theta or theta does not change, and so does cosine theta. So there's still a 2 in the front, so I can still cancel that out. And I can still divide by c, so you find that, or your working equation is dc dt is 1 over c times a dA dt plus b dB dt minus, so it's gonna be a dB dt cosine theta. So I'm just gonna distribute the cosine theta, and also that minus sign at the front, minus b dA dt cosine theta. So I'm just gonna group it here. So it's pretty much the same procedure, except we get to tack on an additional term, which is this term here, which accounts for the fact that it's not a right angle. But other than that, you'll be employing the same procedure with using, this relation over here, dA dt is a of t over t. So that's time rates, or at least our application of time rates here to relationship theory. Yeah, really simple. We didn't need to employ some complex mathematical machinery such as exponentiating a or raising e to an exponent, raising e to a matrix, and actually studying a slope field, right? But in this case, it's just simple manipulation and analysis. So I actually got this problem from a class in Calc 1. So as you all know, of course, I'm in college, and then I'm in first year studying engineering. And the next sem, we're going to be taking on integrals. And I think it's going to be pretty interesting. So this is time rates.